Hello, welcome to the next installment. This discussion is going to be on Euler's equation. You recall back when we demonstrated that pressure was a scalar, we arrived at an equation like this. Rho g minus the gradient of pressure equals rho times acceleration, and this is called Euler's equation. The key point here, let's assume that g becomes part of acceleration, it changes value. We have that acceleration is inversely proportional to pressure. That's really all that we're seeing here. Let's examine a simple example that can make use of the equation that we derived earlier. So we'll have a cart on a path, and it's going to be filled with Wasser, and we will accelerate it at speed a sub x, and an acceleration rate of a sub x constant, so that the water surface in it looks like that. And we know that here the depth is 28 centimeters, and here the depth is 15 centimeters. What value of a sub x will maintain the shape? Okay, so that's our simple question. Let's see what we have known. We know that the depth at position 0 is 28 centimeters, so we're going to call this our origin. We're going to measure x that way, and we'll measure z that way. The depth at 100 units away from z, I guess I need to tell you that this is a 100 centimeter long cart, is 15 centimeters. We'll have gravity accelerating downwards, so g will be minus g sub z. And we know that the material is water. Unknown, a sub x, governing equation is rho g minus gradient of pressure equals mass times acceleration. So let's go ahead and come up with a solution to answer the question. We'll break this into its two component parts. The x component, so there is no gravitational component in the x direction. All we have is minus gradient of pressure equals rho times acceleration, or dp dx equals rho ax. And in the z direction, we'll have dp dz equals rho g. The minus takes care of that issue. And in fact, we can directly integrate this to come up with p equals rho g sub z times h as a at any place, because we're integrating up to the top of the water. Go back to this one. Take the minus dp is equal to rho a sub x dx. dp equals minus rho a sub x dx. And now we'll integrate that from p0 to p100 dp equals minus rho a sub x integral from x0 to x100 dx. Perform the indicated integration, so we get p100 minus p0 equals minus rho a sub x times 100 minus 0. These are centimeters. we now can substitute the pressures here from this. So P100 is rho GZ. Now the H at 100 is 15 centimeters. P0 is going to be minus rho G sub Z. The H at 0 is 28 centimeters. And minus rho A sub X times 100 centimeters. All right, we could actually try to worry about values of G and rho, but this is pretty cool. 15 minus 28 produces minus 13 centimeters. This equals minus rho AX times 100 centimeters divided by rho G. And so instead of actually having to solve for AX, we're just going to solve what ratio of gravitational acceleration it is. This is actually how, when they talk about spacecraft accelerating at 0.5 g and so forth, it's an expression much like this. So we'll divide both sides by 100, and we have minus 0.13 equals minus a sub x over g sub z. Therefore, a sub x equals 0.13 g sub z, or to maintain the shape that was described in the picture, we have to accelerate at 0.13 g's, basically a tenth of a gravitational acceleration. If we want to put numbers in now, we can. We simply have a sub x equals 0.13 times 9.8 meters per second squared, which is 1.27 meters per second squared. It's actually not a trivial amount of acceleration. So from tenth of a g is substantial. I mean, that's a 1 meter per second per second. That was direct application of Euler's equation. So now let's study it a little bit deeper. So Euler's equation of motion for a fluid is mass times acceleration equals gravitational minus the gradient of p. I've just rewritten it, but I put the acceleration on the left. It's valid only when the only forces are gravity and pressure, hence inviscid flow. It's not a bad approximation for some viscous flow situations, the water hammer behavior in a pipeline being the notable example. There's two classical ways that this equation gets applied in practice in the class. One is for uniform linear acceleration, which we've just seen. That was the example I just did. And the other one is for a constant angular velocity. And there's other ways to use it, but these are by far the ones that are discussed in the book. We'll go through some illustrative examples in the next few minutes. And ultimately, we're going to get to Bernoulli's equation. All right, so we'll do the uniform linear acceleration. We're actually going to repeat the last example verbatim, but this time we'll do it a little less haphazardly, I think. Okay, so we're back to a cart again. It's on wheels. It's going to be accelerated with some acceleration that way. There'll be some gravitational acceleration going down. This time we'll do it in real algebra. So the cart has length L. There's some initial depth before the acceleration begins, and then there is some water surface pattern shown right here, X and Z. So it's pretty much the same drawing. The question is different. A rectangular container is subject to constant acceleration. Find the shape of the free surface. In the prior example, we knew the shape. We were trying to find acceleration. So here we're going to try to find the arbitrary shape of the free surface based on acceleration. Essentially the same result. So our fundamental equation is Euler's equation. Break it into its two component forms. Rho a sub x equals rho g sub x minus dp dx. Rho a sub z minus rho g sub z equals dp dz. We will notice that a sub z equals 0. There's no forced acceleration in the z direction. And g sub x equals 0. There's no gravitational component in the x direction. So we now can simplify both forms. So we have dp dx equals minus rho ax. dp dz equals minus rho gz. And to find the shape, we need to consider 2 points on the free surface. So here's our cart again. We have no idea what the free surface looks like at point A and B. We don't know what's going on here. It could look like that for all we know. We have our coordinate system, x and z. But we do know something. This free surface is an air-water interface, at least as we're doing this in land of air. So what we know is that anywhere on this free surface, we know the pressure is 0 gauge. Has to be. More importantly, that means that the pressure at A equals the pressure at B because they're both on the free surface. So the pressure at A equals P, x equals 0, z equals z sub A, an unknown value, and the pressure at B is pressure at position L, z sub B. So we're going to call ZA that value and ZB this value. Okay, the pressure variation is given to us by these Euler's equations. So we have the change in pressure is dP dx plus dP dz dz, which equals minus rho a sub x dx in our case, minus rho g sub z dz. But on the free surface, we know that dP has to equal 0. Now this only applies at the free surface, so we'll underline it in red. doesn't change. And so with that knowledge, we know that rho a sub x dx equals minus rho g sub z dz, or dz dx equals minus a sub x over g sub z. We now can integrate this critter to find the shape of the free surface. And this is very important because we're going to do this again with open channels, where we're going to come up with a relationship that tells us the slope of the free surface. The function is going to be different because we're under different conditions. So this finding a dz dx form is not uncommon in fluid mechanics. Let's go ahead and do that integral. So we have dz equals minus a sub x over g sub z integral dx, and that produces z, the position of the free surface, equals minus a sub x over g sub z times where we are plus c. So now we'll have to evaluate the constant of integration with whatever known values, and we'll consider that at L over 2 that we can specify the depth. Okay, so to evaluate constant of integration, consider depth at x equals L over 2. And suppose that that value is d0. Z at L over 2 equals minus a sub x over g sub z, L over 2 plus constant of integration, which has to equal d0 because we get to pick it. Therefore, the constant of integration equals the mean depth plus axl over gz2, and that now gives us the equation of the free surface. So z, the position of the free surface, is equal to d0 plus axl over gz2 minus ax over gz times x. Let's ask ourselves if that's correct. At x equal 0, that term vanishes, and so at the left edge, it's the mean depth plus some increase. At x equals L, we're going to end up with minus ax over gz L over 2, so it's the mean depth minus an amount. So this makes intuitive sense. Again, here, let's look at our here's our mean depth, d0. We've accelerated it. And so that this part here, that equals axl over gz2, and this distance here is also axl over gz2. This is a general form, so we could have used that to solve the previous problem, and since we have the previous problem already worked out previously, let's see if it actually works. We will apply this formula to the conditions of the previous problem. Okay, so what did we know in the previous problem? We knew that in the prior problem L was equal to 100 centimeters. We know that Z0 is 28 centimeters and Z100 is 15 centimeters. We also knew that A of x was equal to 0.13 g sub z. So let's apply that and see if indeed with this distance, that acceleration, we indeed recover these values. We do need to know what the mean depth is. Well, let's do it as a variable and then see what we come up with. Okay, so we know that z of 0 is equal to d0 plus 0.13 g sub z over g sub z. L was 100. Divide that by 2. And we're at x equals 0, so that's minus 0. So what we have is that g sub z and that g sub z cancel. And so we have this equals d0 plus 13 over 2. And now let's look at Z100. Z100 is d0 plus 0.13 g sub z over g sub z. Length is 100 over 2 minus 0.13 g sub z over g sub z times 100. This equals d0 minus 13 over 2. So this equals d0 plus 6.5. This one equals d0 minus 6.5. And so lastly, we need the mean depth, which in that one was 28 plus 15 divided by 2 was 21.5. So d0 equals 21.5. And indeed, z0 is 21.5 plus 6.5, which equals 28. And Z100 is 21.5 minus 6.5, which equals 15. So either way, we got the same result. By far, the general formula here would be more useful if you had to answer questions like this a lot. All right, so that was constant linear acceleration by direct application of Euler's equation, which we essentially derived when we were showing that pressure was a scalar. Now let's look at the other way of using it, which is uniform angular velocity, or constant angular velocity. We'll have a U-tube-nometer, so named because of the internet sensationalism of it. Just kidding, that's me making a pun. And we're going to rotate it about this tube. So we'll spin it with an angular velocity of omega. Let me go ahead and get my coordinate system put in here because I'll need it. Okay, so Z is up. This will be a radial coordinate system, and we'll have, polar coordinate system. So we'll have some angle and then radius. We'll fill this tube with red. So before it starts spinning, maybe everything's at this level, but after we start spinning, looks like this. And we're interested in this height, delta Z. We know that here this would be height Z1, and this one will be height Z2. So delta Z is clearly Z2 minus Z1. All right, so there's our setup. U-tube manometer is rotated about an axis coinciding with one of the arms. At equilibrium, what's the difference in height of the fluid in two arms of the manometer? And this stuff has to have some density, so we'll give it rho liquid. So again, we'll start with the fundamental equation of motion. Rho g minus gradient pressure equals acceleration. Bust it up into its component form. dp dr plus rho g r equals rho times acceleration in the r direction. So r is that direction. Change in pressure with omega plus rho g omega equals rho acceleration omega and dp dz plus rho g sub z equals rho a sub z. Okay, are there gravitational components in the r direction? That would be no. So that's 0 because gravity acts only in the z-axis. Therefore, that one's also 0. Okay, as for acceleration, there is no acceleration in the omega axis because it's constant speed. So that term is 0. And there's no forced acceleration on the z-axis. That term is 0. We do have to recall back from kinematics that the radial acceleration for constant angular velocity is a sub r is equal to omega squared r. You had that back in mechanics. So with that knowledge, here's what we have left. We have minus dp dr equals minus omega squared r minus dp d theta equals 0 and minus dp dz equals rho g sub z. Let's look at our pressure variation. dP equals dP dr times dr plus dP d theta times d theta plus dP dz times dz. That one vanishes. This equals rho omega squared r dr minus rho g sub z dz. So that's our variation of pressure. Now we're going to integrate this dP term to find a formula, and then we're going to take advantage of knowing that the pressure there and the pressure there are the same. and then that will give us the result that we need. So if we integrate, we have the integral dp equals integral of rho omega squared r dr minus integral of rho g sub z dz is equals rho omega squared r squared over 2 minus rho g sub z times z plus c1 plus c2. Two constants of integration. Constant from that, constant from that. They actually can be bundled together. Probably should be. We'll now find the constants of integration from known pressures on the liquid surface. So, at r equals 0, that's the tube around which everything's rotating, z equals z1, our terminology, that pressure equals 0. That implies that rho g sub z z1 equals c1 plus c2. At r equal cap r, where the other tube is, z equals z2, our terminology. Pressure equals 0. And that implies that rho g sub z z2 equals rho omega squared capital R squared over 2 plus c1 plus c2. We'll subtract this term from that term, and what we have is rho g sub z z2 minus z1 equals rho omega squared cap R squared over 2 plus c1 plus c2 minus c1 plus c2. Constants vanish, and a little bit more, once those constants vanish, that density is unimportant from the standpoint of the remainder of the terms. And finally we have z2 minus z1 equals omega squared r squared over 2g sub z. Now cap r, I forgot if I drew it. Yeah, it looks like I didn't. Cap r is how far apart the tubes are. And that would give us the change in height on the manometer. Okay, that concludes this video, and I will edit and render and then get on to the next one.